guys, thank you for joining. This is the Oracle Machine Learning Office Hours. I'm Marco Sarancibia, and today we're going to see the machine learning concepts and coding of categorical attributes with One-Hot versus mean encoding versus weight of evidence and when to use them. So Jie Liu from our team is going to be doing it, and myself, Sherry, and Mark are going to be supporting. So for any questions you guys might have, don't hesitate to put them on the Q&A. And thank you very much, G, for joining. And take it away.
Hello, everyone. Today we'll talk about the topic for categorical variable encoding, and have a brief review of the popular techniques. And then the main part is I want to share with you some recent findings with weight of evidence, what our experience and how to better use that, and also show a little bit of the code in the notebook of how to implement it using OMF4Pi. And that's the outline. So as Marcos pointed out, the categorical variable encoding is every data scientist need to do almost every day. So conceptually, so what is a categorical variable? So comparing to numerical variables, the categorical variables are those variables with one or more categories and levels. They often are discrete, not like numerical values, they are continuous. So they have a discrete categories and levels, and oftentimes there's no order in it. For example, see some categorical values have like high, medium, low, or like they naturally have orders, so you don't need to worry about too much. You just can translate them into numerical values very easily. For example, we have like the marital status. We have four levels: married, single, divorced, widows. There's no way to impose orders in it. So why we need to do the encoding? Because nowadays, most of the ML algorithm, they need the numerical input. A lot of the ML algorithm, like SVM, they are formulated as the optimization problem on numerical values. You still have to do that. They only accept numerical input. And even for some algorithm, like a decision trees or random forest, they can accept the categorical variables, but they have a limit, actually. On most of the implementation of the random forest, they have some limit on the number of levels of the categorical variables. If you have like 1,000, hundreds of levels, they won't do. So that we still need to do the encoding. There are several popular techniques for encoding the categorical variables. The first of it's the one-hot encoding, of course. So the idea is, we want to convert each level to a column, just like doing pivoting. For example, here, originally we have 4 levels. Now we have, each level as the column here. And originally for each row, if it belongs to one of the level, like being divorced here, then you assign 1 and 0 as the others. So that's why the name is used. Like we only have 1 as 1, and all the other are 0. That's why one-hot, what we would call one-hot. So this technique is widely used. I think one of the benefits is there's no information loss. You didn't lose any information. It keeps the original, all the information. And one thing I want to point out that if you stick with the Oracle machine learning algorithm, in database algorithm, you don't need to worry about that. You do need to do that manually. So all the algorithm can handle that. So these transformations are automatically handled in each algorithm. The drawback of this algorithm apparently, it ends up with a high dimensional feature. If right now we only have like 4 levels or 5 levels. You have so many columns. But imagine you have a very like 100,000. You probably have a very high dimensional feature. And that gives us some trouble, right? What we call high cardinality feature. And sometimes when the feature number of features can exceed the number of rows, that's called overfitting, and also have a higher computational cost. So then we wonder if are there any other techniques that can solve this high dimensional problem. One of the popular techniques people are using are called mean encoding. This idea is very simple, but actually kind of effective. A lot of people are just are using it. So we can keep the original number of columns by just encode each level to a numerical value. So that's the idea. So how will you do it? We do it, by calculating the conditional probability. For example, here, like suppose we want to predict a binary flag for the buy insurance, whether people buy insurance or not. And if you want to encode the marital status feature, so we naturally want to calculate among the people who married, what the proportion of them who bought the insurance. So this gives us some idea of, if once we see the data, the people have married, how likely, they bought insurance. So that's why we calculated the conditional probability here. Like given the people is married, what's the probability of, they bought insurance? So naturally, is to keep the same feature dimension, it has a low computational cost. But the one thing is they may lose information, right? You can imagine there will be maybe 2 levels. They have the similar probability. Then you will see you will see these 2 levels are being almost the same. So you still lose some information here. And beyond that, we can see there's more issues with that mean encoding. So the one issue is is kind of sensitive to the target distribution. For example, so on the left, this is our distribution of the buy insurance. So naturally, it's originally, the number of positive cases are roughly about one third. It's not that bad, and it means the mean encoding score here, reflects roughly that, and we have reasonable values here. But what if we throw away a lot of the possible positive labels and we create a highly imbalanced data set? Like we only keep position positive cases to 10%. This data set then became imbalanced, and this is create trouble, of course. And this mean encoding score, you can see they changed with the target distribution. Right now they all drop to a very low value, and this is not ideal. This is because all the encodings look the same, almost the same level. So we keep asking, are there other better encoding scheme? Today we probably will focus most of our time on explaining the idea of using weight of evidence. It's not a new idea. A lot of the people are using it, especially for credit score model analysts. They're using that quite often. And but the interesting is that from a perspective of category encoding, we can see there are several benefits of using that. So this is the definition of a weight of evidence. Basically, it's like a log ratio. And if you look at the denominator and denominator, right now we have little kind of a switch of the role of the feature and the target. instead of calculating the conditional probability of giving a feature what its target probability, now we switch the role. Now the interpretation is like among the people who bought insurance, how likely are they married? And then we look at among the people who did not buy insurance, how likely they are married. And then we compute the ratio and take the log. So it's kind of doing that reversely, right? The one thing I want to highlight is that like it's doing the ratio kind of make a better contrast of the positive and negative impact. You know, the reason why we create features is that we hope this feature can indicate whether this example belongs to positive or negative. So now by taking the ratio and then take the log, you know, this make it have a better contrast. So we can compare this values here. On the left, we have a weight of evidence, and on the right is mean encoding. And you can see that, you know, we can directly see that the single person, you know, they have an active values here. So this is naturally indicates, you know, maybe among these people who bought insurance, they're not too much single person. For the mean score, this is very kind of low, but it's not that obvious. So that's one of the benefits of for the weight of evidence. And there's more. If we want to dive into the formula, and we can find something more interesting aspect. The question is, since doing the log ratio is beneficial, why not we just doing that on mean encoding, such as this, right? Each of the denominator and nominator, nominator and denominator, they are actually the mean encoding, and we do the ratio and take the log. However, if we look at further, so this term can be actually split into two. So on the left is actually the target, all about the target distribution. And this term does not change with any feature level. And on the right, you know, we are kind of familiar because this is the you know, weight of evidence. So that this indicates that if we simply do the log ratio of mean encoding, you always have this impact of the target distribution, right? And this part is not that useful to us because what we want to focus is whether this is we want to focus the contrast, right? The contrast of whether to be positive or negative. So the weight of evidence actually are like throwing away this part, right? We only focus on the part with information with the feature level. But this naturally gives us the benefit of you know, this naturally does not have now the target distribution does not have a big impact. And we can see from the proof, like from the numerical examples. Again, on the left is the one with the regional data. On the right is that the one with only 10% of the regional positive cases. And we can see that not too much changes in the values, right? So this is insensitive to the class imbalance, which is good for us. Although they have the weight of evidence have a lot of benefits, still it has some limitation because this is the ratio. It is naturally only works for binary classification. And if you want to do the multi-label classification, either you use the one with vs the other techniques. You know, if you still want to use the weight of evidence, it's like you predict. You have 10 classes. You keep creating 10 models, only predicting, you know, whether to be class 1 or other, class 2 or other, yeah, something like that. In that case, you may be able to use the weight of evidence, or otherwise you just go with One-Hot and mean encoding. Yeah, that's so one limitation. Beyond that, beyond the weight of evidence of you know, beyond the feature levels, we can actually go up a little bit, right? We go up to the level above it, which is the level of features. The idea is we can calculate the concept called the information value. So we do the integral, or like we calculate the sum over all the features, and therefore we can calculate an information value for a particular feature, and that can be actually used as a measure of feature importance, which is quite useful. As I mentioned earlier, the credit score analysts are using that, and they have some rule of thumb. This is from kind of like a well-known book about the credit score. So they have there's some rule of thumb of this information value to indicate whether this is important to make the prediction or not. You can see that if you less than this value, maybe not non-predictive, and they have a weak, medium, strong, and this is the kind of empirical rules. And we can certainly use that, as a way to measure the feature importance. So since the weight of evidence is very useful, the question is how we compute it. Prepare several code, to implement this, use OML for pi transparent layer, to compute the weight of evidence in a scalable way. Those all the details about the how to implement it can be found in one of my blog. So today, I will. So next, we will go through the notebook and to show you some more interesting stuff. So yeah, this is the OML notebook, and so this paragraph contains our code of calculating the weight of evidence. Yeah, I added a function also calculates the mean encoding as well. I will not go too much details into this code, and more detailed step-by-step instructions or information can be found in this blog. But one thing I do want to highlight is that when we implement this one, because you want to calculate log ratio, thing is you do not need to calculate the ratio, because when you calculate the doing the divide, you may end up with the numerical precision problem. Sometimes you may see error, because when you divide two very small values, that may be you may end up trouble, because that's sometimes may be already out of the precision. But the benefit is here is the log ratio can be converted as just calculate, convert it to a sum. You do a log sum instead of doing the ratio. So it's one, as you can avoid the numerical instability. Yeah, so right now, we can have a closer look at the data here. So we have marital status and all these demographic features, and the goal is to predict whether they have whether they buy insurance or not. We can do some transformation, like originally say yes and no. For convenience, we can convert it as 1 and 0. Yeah, one thing I want to highlight is that since we all talking about the categorical encoding, so you probably need to figure out which column is categorical or which column is numerical. OML for pi is easy. You can choose use this function called select types, because all the categoricals should be encoded as the strings. So this is the float. And one interesting thing is the weight of evidence only always work with the categoricals how about the numerical columns? The answer is easy. You can just bin them, right? You bin the numerical variables to convert it as categorical variable, and you can calculate its weight of evidence. But this is the choice of the users, right? If the user just want to use the numerical inputs directly, you don't need to do that. But if you still want to calculate the information value and the weight of evidence, probably need to do the bin first. So yeah, this can provide some contrast of some examples of the actual columns. We calculate the mean encoding and the weight of evidence values for marital status. Yeah, you can see the values. And also we pick another column called region. And that's give us better idea, even better idea. We can, let's see these negative, positive values here compared to the mean score. So yeah, this is the example of doing the imbalanced. If after we change the data set to an imbalanced data set, what will happen? Yeah, so this we can see the weight of evidence didn't change too much here. Yeah, so this code calculates all the information values of the columns, and yeah, we also touch the level. Yeah, some are weak, some are medium, and we can rank these features. Yeah, it seems that the profession are like the most predicted feature, number of dependents. And yeah, the next is since we talk about about the weight of evidence transformation, how this looks like when we apply it to the actual classification task. So we use all the weight of evidence features and try to see what will happen. Yeah, we split the table into train and test. So we want to train the model on the training test and to see the results on the test data set. So here we train start from easy the simple model and try to see the impact. Yeah, after we build the generate linear model, we can get get predictions. So and then we can generate a visual to check the results. So this one is all with the evidence transformed feature. You can see that here it's our familiar, our old friend, the ROC curve, and you can see that you see we obtained this 0.73. It's not bad. So now the question is, how about we use the regional feature, right? So here we use the weight of evidence feature. So this is always good to make a comparison. So here, yeah, we want to make a comparison. We need to stick with the original split, right? We need to train the model on the same training data set and also test on the same test set. So to do that, I need to do use the join here through the transparent layer to make sure we were doing, doing the building model, test model on the same split. The same thing here, we build the generate linear model, keep the original training data, and we get the results. So this is using the original data without any transformation. Now, yeah, we can see that it's this is lower. And that means, our weight of evidence actually give us a boost in this performance. And we can get a better view, right? We can plot the ROC curve altogether here. And the blue curve is the weight of evidence. It gives us some boost. And I would not say that weight of evidence can always give you a boost in improvements in the classification performance, but based on my experience, in our at least in my one of past projects, it provides a decent level of improvements. And of course, if you are interested, you're more than welcome to try on your side to see, if the weight-of-evidence transformation can give you a better accuracy. So and sometimes even it's not that, you think the performance is no better, but remember it still have the benefit, right? You still enjoy the benefit of reducing the computational cost, and also even you do not use the weight-of-evidence transformation, you can still enjoy all the benefit of better interpretation, like information value, and can use that for selecting the variables also. I guess that's that's most of my presentation. So I'm not sure if I still have some time, whether it's still need to answer some questions or.
Excellent. Yeah, thank you very much, Jie. That was very, very good. And so we have two questions actually. The first one here in the Q&A was, what's the suitable encoding scheme if the dimensionality is highly granular?
Dimensionality, it's the.
Yeah, so if you have, zip code, right, and things like that, where you have too many dimensions, right? Or
right.
So,
yeah.
So that's the idea.
Yeah, that's if you have like a very granular. I believe the weight-of-evidence and mean encoding, this kind of flavor encoding scheme should be better. You definitely want to avoid to generate too many columns, thousands of columns. Yeah.
Oh yeah, absolutely. Yeah, no, totally. And for sure, One-Hot Encoding is gonna be too much for any algorithm to make sense of it.
Right. Yeah.
Yeah, that's perfect. And then other than that, people asking for us to share the notebooks. So what we're gonna do, guys, is we're gonna share the notebook from Jie to the GitHub repository that we have. So hopefully by tonight or a couple of days maximum, the GitHub is going to be updated with the example there as well. What else? Any other questions, comments, guys? Okay, excellent. All right. So thank you very much, guys, again, and I'll see you guys next week. We're going to be doing a Machine Learning 101 hands-on lab. It's probably going to be an hour and a half next week. I'll try to get it, cram down it to an hour, but we'll see how fast we can go through it. Okay. So thanks a lot. Really appreciate you guys for joining. And as always, if you have any questions after the session is done, you can go back to the link that you used to join us here, because you can actually submit questions there. Okay. So thank you very much, Jie, again. Excellent session. Really appreciate it. And have a great day.
Yeah, thank you.